So there was a request for working on problem number 11 from the homework, whoops, not 17, I think it's homework 20, the radical homework, and then question 11. This is not going to be a complete solve getting all the way to the answer, but it should help you get most of the way there. We're looking at radicals, so big tip off that we're looking at radicals. You see NBS, which is primarily a radical reagent, and then our other big tip off is that we're looking at HNu, which represents light, and then our ROR represents a radical initiator. Okay, so, and then, officially, another big tip off is homework 20, which is all about radicals, but beside the point. So when we look at our reagents, we know we're looking at radicals. NBS supplies bromine. So we are looking at a bromine radical potentially going through and doing this reaction. One of the things that's nice about the NBS is it generates bromine in very low concentrations, which means we end up seeing a standard radical reaction as opposed to the addition reaction that we'll talk about after exam 3. So, with that low concentration of radicals, what we are looking at doing is pulling a hydrogen off of our starting material. And in particular with NBS, what we're concerned about is pulling hydrogens that are from the allylic position. So the allylic position is one carbon atom away from the double bond, and that's why I picked those two hydrogens. So either of those are fair game, because we have this resonance stabilization to stabilize that radical, which makes at very least two possible products to come out of this. Okay? And the big tip-off that we've already kind of mentioned is getting those other products has to do with resonance. Okay? So let's take a look at the two primary ones. If we've got our radical, and I'm just going to, for the sake of drawing it, just say R for our radical. It can go through, share one electron with our hydrogen, and we end up with one form of our radical. Whoops, I should actually draw the structure appropriately. Looking at the cyclopentene ring, we would have a radical at that position. If we went through and looked at our other position, which I'll attempt to again color code, we could have our radical come in, take electrons from that hydrogen and put our radical there. So we end up with two possible intermediates. Between these two intermediates, we might say that our blue one is favored because it's a tertiary allylic, and our purple one is a secondary allylic. We have to be a little bit careful with this because once it's allylic, both of them are relatively stable, which means both of them are going to be possible products to come out of this. What they're focusing on within this problem is looking at all possible products that have relatively high stability. So both of these are going to be probables. The final stage would be our bromine radical, which for simplicity I'm just going to show with a single electron. Could come in with our secondary allylic to produce, let's go through and color code again. Can come in with our secondary allylic, and we can get our purple final product, which would be this guy with our bromine there. We could also have our bromine radical come in with our tertiary allylic, and we end up with this final product, our bromine here. So hopefully you're able to identify those two right away. Where the next two products come from have to do with resonance coming from your blue and purple structures. So since in theory you understand those products, I'm going to go ahead and erase all those arrow motions, and what we're going to do is look at that resonance contribution. Oops, I erased my radical there. So one of the reasons why the allylic position is so reactive is because it's resonance stabilized. I can take that single electron and move it into the space between those two carbon atoms, and I can take a single electron from my pi bond and do that same deal. Okay, the result is that we end up with the pi bond here. Okay. You'll notice that we are missing some information because what I've just got drawn here does not have a radical. Well, if we go back to our structure, what we did was took an electron out of that pi bond. We took one electron out. What did we do with the other electron? It can't exist in that same bond space because for us to draw it as a bond, there has to be two electrons, and we got rid of one of those electrons. So what we'll do is show where that other electron went, and that other electron went to that carbon. So the result is we end up with our radical at that position, and we now have a resonance structure for our purple radical. Now you would have to go through and see what would the possible product be that would come out of that, and I'll leave you to figure that one out. With our blue situation, we're going to go through and do the same kind of idea. We can take that radical and resonance stabilize it by having it interact with that pi bond. If we again draw out our possible intermediate, we'll have the pi bond located there. Again, we have that issue. We don't have the radical, so what happened to it? If we go back and evaluate our pi bond, we only took one electron out of it. That other electron, we have to specify where it went. It went to that position, goes to its partner carbon, and we have the radical located there. With these two products, we could now go through, or with these two structures, we can now look at the possible products that come out of this. And that's where it gets a little bit trickier, is then looking at all your multiple choice options and trying to pick out which ones work and which ones don't. At this point, we really only have 4 intermediates. Let's go ahead and mark it in orange. We've got 1, 2, 3, 4. Are any other positions reactive? Okay, well, there's a lot of other hydrogens, but those other hydrogens aren't stabilized by the pi bond. They don't have, and since they don't have that additional resonance stabilization, they aren't likely to form, so we won't look at those. You can continue to try and draw resonance around, and what you'll find is you'll only oscillate back and forth between these partners. So for our purple structure, we'll only oscillate between those two resonance positions, which means the radical never makes it to any one of the other carbons. If we take a look at our blue structures, we'll notice the same issue. It can only resonate between those two structures, which means no other position has the radical, no other position can actually put the bromine on. Okay? So when you go through to evaluate your problems, draw out the structures, draw out the resonance contributors. Okay? That's one of the reasons that you have to be very careful with the SN1 and E1 reactions, because we have a carbocation. What did we say back in the beginning of our radical lecture? Our radicals act very similarly to our carbocations. So if carbocations can do resonance, so can our radicals. Draw the resonance structures. Okay? That's how you'll decide what those other products are, not just random guessing, okay? Which I'm sure people are going to be willing to go through and do with this, but try and draw the structures to get your correct answer. Okay? Hopefully that gets you your answers on that. If you got any other questions, just send me an email and I'll see what I can do about drawing up a little tutorial.